So last session we stopped here with transformer XL. The idea was you wanted to extend the limited context of transformer architectures to an extended context. We managed to do so, and at the same time, we needed to take care of the positional encoding. Rather than using absolute positional encoding, we are going to be using relative positional encoding. And actually, one of the reasons I go through this paper is to introduce the relative positional encoding concept. Any questions about Transformer XL before I continue? Okay, so far so good. Let's move on to XLNet. XLNet is going to be using the Transformer XL architecture. So we are not going to be focusing on that part of the architecture anymore. We are going to be focusing on other parts. So the video is online. We can go through that. But now I'm going to give you an overview, and then you can ask questions. So this is going to be a quick overview. What have we been doing so far? We have been going back and forth between the encoder part of a transformer and the decoder part of a transformer for language modeling. And that was deliberate. So one slide was about the encoder, another slide was about the decoder part of the transformer. Some of the models were autoencoding, some of them were autoregressive. For instance, BERT type of models are gonna fall into the category of autoencoding, and GPT type of models are gonna fall into the category of autoregressive models. The cool thing about XLNet is that you can actually marry the two. It turns out that under one umbrella, you can explain both of them. So what are we doing? For autoregressive models, you are gonna choose a permutation, and that's a particular permutation. That's gonna be the permutation of numbers from 1 up until capital T, and that permutation is just 1, 2, 3, 4, 5, 6 up until the length of your sequence. And then you're gonna use chain rule for probabilities to write down the probability of your sentence. Another permutation is to go backward, which is gonna be T, T minus 1, T minus 2 up until 1. But these are two specific permutations. You can have all sorts of permutations for your input indices. And the idea of XLNet is there is nothing special about forward permutation, backward permutation. You can actually use any permutation that you like and average them out. In that way, XLNet is generalizing autoregressive models. At the same time, for autoencoding type of models, like BERT, you're going to mask out a couple of words or subwords in your sentence, and then you're asking, give me the correct word here. What did I mask? And that's the job of the language model, to tell you what was the thing that you masked. But there is a problem with that. This mask token is a specialized token for this particular pre-training task, and it's not going to show up in any of your downstream tasks, or it's not going to show up on the ones that we know of. So there is a bias towards this mask, and we saw that BERT was actually was aware of that problem and was trying to deal with that problem by picking 15% of your tokens. Out of those 15%, 80% of them you actually mask, 10% of them you do nothing, and the other 10% you're going to replace by a random word in your corpus, in the hope of reducing the bias towards this mask. Using this idea of permutations, you can actually get rid of that. How? You choose a permutation, and according to that permutation, some things are going to be the past, some things are going to end up being the future. For instance, is a city is a past, and new is the future, according to that particular permutation. And then as you go to the next step in your time, the next token in your sequence, which is permuted, new is a city is going to be the past, and York is going to be the future. Or this could equally likely be the case that is a city is the past and York is the future, and then York is a city is the past and new is the future. And this way, mask is not present during training anymore, this mask token. And your model is not going to be biased towards that mask token. That's the entire idea. But implementation-wise, things are a little bit more complex than you think. The idea looks simple on a piece of paper, but when you want to implement it, you need to be careful. First of all, you don't want to have a new architecture for every permutation that you write down. You want to work with a single architecture. And at the same time, when you are predicting a word at a particular location, you are not allowed to look into the future because this is actually an autoregressive model, and the future is based on your permutation. You are not allowed to look into the future in any form. You are not allowed to look at the word. You are not allowed to look at the subword. You are not allowed to look at the representations of that word in any of your layers, because that's going to be cheating. But at the same time, you need to know the index. Where are you predicting? Which word are you predicting now? And because you want to get away with a single architecture, and you don't want to keep rotating these indices around and have multiple architectures per each rotation, per each permutation, you need to have two types of streams for information. One of it is the content, which is going to build the content upwards in your hidden layers. These are these H indices, or these H hidden units. At the same time, you have a query stream, which is not allowed to pay attention to itself. Any questions about XLNet? So most of XLNet was about the loss function that you're going to write. At the same time, you wanted to marry autoencoding and autoregressive and explain them under a single objective function under one umbrella. And there was some part about the architecture design. And that architecture design is because of the challenges that you have when you permute. And you don't want to work with multiple architectures per each permutation. There is a question about how are query and content streams merged. That's actually a good question. There is a query stream, there is a content stream, and let's look at what each one of them is doing. The content stream is creating your age vectors. It's going to take the past age according to your permutation. The query is still age, and age is going to represent your content, and then it's going to output your age. And this is going from one layer to the next layer, from the previous layer to the layer above. And these are these blue squares. And initially, these are just your word vectors. So you know how to initialize them. You know how to handle your permutation by permuting your masking strategy. And then from one layer below, you're going to the layer above using this formula. And that's going to give you your H from one layer to the next one. And that one you can construct all the way up to the last layer. What else? Let's look at G. G is not allowed to look at X in any form, but it's allowed to look at Z, the location. And that's exactly what you're doing here. Your query is coming from G. G is initialized with some random vectors, where it's actually the same random vector for the 0th layer. And then the next layer, your query is going to come out of the G. The key and the value are going to come out of your H. And this is exactly what you have here. And this H, you're not allowed to use the teeth location. So this arrow here is absent when you're creating your G. And then you create G all the way up to the end. But once you want to do your prediction, you're going to be using G. You don't need H anymore, because the information that you need is already in G through this attention mechanism. So there is no need to concatenate them. There is no need to just keep two separate streams next to each other.
So at each level, then G is generated using the H of the previous level.
Exactly.
Okay. So it's almost like merged throughout the entire, at every level, there's some kind of, okay, thank you.
Yeah, exactly. So you have the previous layer. In the previous layer, you know your H. At the same time, you know your G. And now you're going to the next layer. From layer M-1, you're going to layer M. And the figure is a little bit confusing. It might give you the feeling that you're concatenating stuff together. No, you're just pushing two different streams upward. And then in the last layer, you're going to be using your Gs, which are paying only attention to the past and not the present. Okay? Does that answer your question?
Yeah, thanks.
Okay, perfect. Any other questions? Okay, cool. This was a brilliant idea. This is a brilliant paper because it's managing to put two different frameworks under the same umbrella.